Hi there, I'm Mehdi, master student in Concordia University in Montreal, Canada, and I'm very excited to share our recent research entitled of Not So Immutable Upgradeability of Smart Contracts on Ethereum with you in WTSC workshop. And I should say that this is a joint work with my supervisors, Dr. Jeremy Clark and Dr. Mohammad Mannan. In software engineering and software maintenance, we have two important concepts. Updates happen when one need to correct faults, bugs, or small changes in the code, and upgrades happen to improve code and like performance and like adding new features or functionalities. Smart contracts are pieces of software that are deployed to the blockchain, such as Ethereum, and supposed to be immutable and tamper-proof. Like it means that if Alice puts a piece of code, or better to say bytecode, in the blockchain, it can be changed. It cannot be changed in the future. So we have a piece of code that cannot be changed, and it is like not compatible with update or upgrade concepts of software maintenance. And in blockchain, it is even worse than traditional softwares because smart contracts have control over billions of funds in their custody. And if the code is buggy, what may happen? A hacker may find a way to exploit it and like drain the whole money. And in some cases, like the DAO hack in April 2016, there will be a race between white hacker to save the fund and black hat hacker to like steal the fund. So no way, we need upgradability feature in smart contracts like traditional softwares, but there are two main questions raised here in this regard that we try to answer them in our research in this paper. The first one is how to deal with the immutability and add upgradability to smart contracts. And the second one is who will be responsible, who is the decision maker for upcoming changes for the system. We answered the first question by studying different upgradability patterns in the wild, and I give an evaluation of them in this paper, and then investigate for the agent who's responsible for the changes of the system. It is also known as admin. This is a big picture of different upgradability patterns in Ethereum right now. And like because the time of this talk is limited, I cannot go into detail of all different patterns here, but I'll explain them briefly. And like for more explanation of these patterns, I suggest you to read our paper. We classified different patterns into two main categories. Retail changes in which one can change a small pre-specified part of the dApp, and the wholesale changes by which like anyone can, the admin can change the whole logic of the system, not just one part. The first method is parameter change. In parameter change, there is some limited number of variables that is in the system design, and like the logic of the system highly depends on these variables, and like changing these parameters and variables will lead to like changes in the logic of the system. For instance, in DAI, there are different parameters such as, for example, stability fee or DAI saving rate, and like admin, which is a governance scheme here, can change these variables, and like by changing these variables they can control the demand and supply of DAI token. The next method is functional component change. In this method, just one component of the system is changeable. For instance, in Compound Protocol, which is a lending platform, in DeFi, there is a need to calculate borrow and lending fees. This calculation is outsourced to another smart contract. And if it is decided to change this formula for fee calculation, then admin can just deploy a new contract with like the new a way of calculating the fees, and then change the pointer to point to that new smart contract. And this is how you can like upgrade the system using functional component change. The pros and cons of retail changes method is like it is very simple to design. It is easy to audit. But the disadvantages are the team cannot fix a bug, and like in parameter change, one cannot add any new logic, and in functional component change, team cannot add new functionalities or new features to the code. So in lots of cases, we need wholesale changes, and the first way of changing the system, the smart contract logic, is doing something we call consensus override. And blockchain specification and rules such as immutability is enforced by a consensus between miners or validators of that blockchain, both technically and socially. And if miners decide to bypass one of these rules, such as immutability, uh, for example, for changing the state of blockchain, they can come up with an agreement and do that. And we had exactly the same event in Ethereum in April 2016 in Dow fork incident. And there may be another same events in the future in Ethereum or other blockchains. The next pattern is migration plan. Migration plan is an easy as deploying a new smart contract, collecting funds and data from the previous version and pushing them into the newer version. It is also called social upgrades. Why? Because there isn't any on-chain clue of the upgrade. There isn't anything on-chain that you can find out that okay, there is an upgrade happen on the blockchain, and the team should reach out to the users and make them aware of this upgrade event. So we call it upgrade, social upgrade. In literature, I can say people call it social upgrade or social yield. So migration plan is costly because of need of pushing data from the old version to the newer one. And in most cases, users are responsible to move their funds or their data from the previous version to the newer one. Also, one cannot fix bugs in the previous version, and at the end, we have two different versions of the dApp that will exist forever, and it's kind of competitor to themselves. For example, we have Uniswap V2 and V3, both of them are alive, and liquidity are split between them, which is not good. The other method for wholesale change is Create2-based Metamorphosis. We won't talk about the details of this pattern. It is discussed in this article, which will be presented in this WTSC workshop. But to briefly explain that, this is a pattern that uses Create2 opcode in Ethereum in EVM, and there's a factory contract which uses Create2 opcode to deploy a magic bytecode, and this magic bytecode can generate new smart contracts. The key part here is this magic bytecode that will create new desired bytecode for us, and this Create2 opcode. So for upgrading the system, the admin should be able to remove, or let's say self-destruct, one of these child contracts, and using self-destruct, as I said, and then put a new contract in that specific place, in that specific address account. But this time with a completely new logic. The factory contract here is a specific type of factory that is called Metamorphosis Create2-based factory contract. And for more details, please take a look at our paper. The pros of using this method is that you can change the whole logic and the state of your contract with this pattern. Developers do not need to change their code to add this pattern to their code base, and the user endpoint won't change after the upgrade. And the disadvantage of using this method is that there is a huge debate on removing the self-destruct opcode from EVM, which raised by Vitalik Buterin. And this self-destruct is a prerequisite for having this method. And this pattern requires having self-destruct, as we discussed. Also, all upgrade events in all upgrade events, the state will be gone, and there is no way to keep the state. And also there is a downtime in the upgrade event between self-destruction and putting the new contract. The latest method for upgradability is data separation pattern. In data separation pattern, we divide the smart contracts into two main parts. One keeps the logic, and the other one keeps the data like a database. So in the upgrade event, just we can change the logic contract and like keep the data and like keep the storage contract. Uh, the most important thing here is how like these two contracts are communicating. There are different ways in Ethereum that smart contracts can communicate with themselves, but the most widely used two ones I can say are call and delegate calls. So there's a call based and delegate call based pattern data separation patterns. Uh, like in call-based patterns, in this type of upgradability pattern, users should send transaction into a logic contract, and the logic contract do the logic, the whole logic that it needs, and whenever it needs a data, it will call a getter function of the storage contract to fetch that data. And like in the event, if the logic contracts need to change a state, it will call a storage contract setter function and like change that state variable. A storage contract will use access control and just let that specific logic contract to change its state. And like in the upgrade event, admins will deploy a new logic contract and change the access control in the storage contract to define the new logic for the storage contract. This is how upgrade will be done in this pattern. In a call-based pattern, there is no need to migrate data, but it's hard for developers to add this pattern to their codes because there's a need to split logic and storage part of the code, uh, and like it will be worse if your contract needs like complex data structure, for example, like mapping or structures. Also, the endpoint address will be changed, and it will break composability. And like it is not that much user friendly because each time you have an upgrade, users must use a new address. And also, the developers must deal with the old version, like pause it or like make it uncallable or doing something like that. The next and the last method is delegate calls data separation pattern, also known as proxy pattern. In literature, people call it upgradable proxy pattern. Here, users will send transaction into a storage contract, or better to say, proxy contract, and the proxy will delegate call into the logic contract, also known as implementation contract. Uh, Delegate calling keeps the context and like it is very similar to copy pasting that specific part of the logic into the contract and run that specific functionality in its context. In the upgrade event, admin must deploy a new contract and like change the target address inside the proxy and let it know that it should be delegate call into the new address, not the previous one. So, pros of these proxy pattern is that one can change the whole logic and there is no need to like migrate the data, and it is like very easy to add this pattern to regular code, and user endpoint won't be changed. Also, there is no downtime in the upgrade event and no need to like deal with two different dApps at the end, and this is why this pattern is popular and widely used in Ethereum right now. And the a disadvantage of using this pattern is like there is a gas overhead for transaction because of the indirection and like that delegate call that needs for all transactions. And also there are some risks due to using delegate call opcode, like the function selector clashes, storage clashes, or you cannot use constructor in the implementation contract, which we talked in detail in our paper. And you cannot change the state. Like if you want to change the state, you should use migration plans. We summarize these methods and like evaluate them in the paper. I suggest reading the paper at the appendix regarding this part because we compare different methods from designer's point of view. Next part of the paper is measurement study. Our main goal in this part is to find contracts that are using delegate call based pattern or just proxy patterns in the Ethereum. To give more details about proxy patterns, just take a look at this snippet code that I add to this slide. And like the proxy patterns are very similar to this. There is a target address, we name it imp here, and like there is a function, fallback function inside the proxy, and like fallback function is a specific type of function, and like if a transaction calls a function that doesn't like exist in the contract, fallback will be executed. In the proxy contract inside fallback, the whole like message, the whole data of the message will be delegate called into that target address. Also, because we need a way to upgrade the system, there is an upgrade function inside proxy which lets the admin to like change the target address and change imp variable. But changing the target address can be done also using implementation contract, and like this type of proxy is called UUPS proxy. And like just you will move the upgrade function into the implementation contract. So to find the proxy patterns in the wild, we use data of 1 year of Ethereum by getting transaction traces of 2 million blocks of Ethereum blockchain from an archival node. And transaction traces are like an aggregated data about the execution of transaction and like consist of sub-traces. Like each transaction may have some sub-traces, and each sub-trace has a data for that specific action about that transaction. And there will be a call type in that sub-trace if that smart contract communicate with another one in that specific sub-trace. So we pick transaction subtraces and like search for subtraces in which we have delegate call, and like if we found that subtrace, we pick them and check for the data field of that subtrace. If the data field is like equal to the data field of the previous subtrace, it means that like this transaction went through a proxy because like there was a fallback inside that contract, and like in that fallback the whole data is transferred to the next contract. So it's a proxy contract, but you know not all proxies are upgradable, right? So we should be sure that there is a way in the code that let admin change the target address. And if there is a way, then the proxy is upgradable. And if not, it is a simple forwarder that will just like forward all calls into the one specific contract for the rest of its life, and there is no way to change that address. So we should decompile the bytecode of that proxy contract and search to find the upgrade function. And if we found that upgrade function, it means that the proxy is upgradable. For the details of the implementation and how we try to find the upgrade function, please take a look at our paper. For the remain proxy, we check if the target address comes from an external call. And like if yes, it means that the proxy is using beacon pattern. And also like each time it will call the beacon contract to get the target address from it. So we mark it as beacon proxy. But as discussed before, it is possible that the upgrade function resides in the like implementation contract and not the proxy. So we need to like find UUPS proxies as well, and this time we will decompile the implementation contract instead of the proxy, and then we will check like to find the upgrade functionality inside the implementation contract. And if we found that upgrade function, then it will mark this like contract as a UUPS proxy. In this research, we found 1.4 millions of proxy contracts, and like we filter them to have proxies that has unique implementation contract. We filter them because you know there are some dApps like OpenSea that creates a proxy for each user, and if we don't filter them out, then it will be counted number of users and not the number of dApps. And like at the end, we totally found 7.4K regular upgradable contracts, 403 UUPS contracts, and 352 beacons. So we answered the first question on how to add upgradability, and now let's take a look at the second question on who's responsible and decision maker for like changing and upgrading the system. There are three main types: an EOA, which is one address, a multi-signature, M out of N% can do the whole thing, and decentralized governance scheme, like each in which members of a decentralized autonomous organization or like a decentralized scheme can decide on the change. There is also another way in which a proxy could like be an admin. It just adds a level of indirection, and like at the end, one of those three types are admins. Actually, the first two types are very dangerous, especially the EOA one, because like in these types, one or just limited number of persons can decide to change the whole logic of the code and may try to steal the whole funds under control of the smart contracts. So we try to find the admin types in the proxy contract in this measurement part. The first step is to find where the address of the admin is saved, and like in the smart contract storage, like we should try to find the storage number. In the contract that follows 9067, the address is saved in specific standard storage slot, but for non-EIP 9067, we should first find this like storage number. And like here in EIP 9067, because we know the storage slot, we use if get a storage at method of an Ethereum node to find the address variable that is saved in the storage slot. This address is our admin address, and like it can be EOA or a multi-sig, and we will find it out using like if get code method to find out if there is a code in it, then it is EOA. It is not an EOA, and if like it, we will check if it is a gnosis safe valid, multi-signature valid, or if not. And if not, we will check if it is a proxy admin contract, and like if it is not a proxy admin, then we will tag it as governance or other types. And for the proxy admins, we will do the same like step from the step one to find the admin types of the proxy admin contract. And for non-EIP 9067 contracts, we should find a storage slot in which the admin address is saved. And for this purpose, like we first find the upgrade function, then check the access control inside the function to find out which address is authorized to call this function. And this address is our admin address. And for the rest, it is very similar to EIP 9067 class. And we find the admin types of them. For more details, please take a look at our paper. And this is like the total result which we can find in you can find in like table 3 of our paper. And totally out of 7.4 regular proxy contract, about 50% of them are controlled by just an EOA, and 30% is controlled by a multi-signature. And this is an alarm to the Ethereum community and ecosystem, because like EOA admins are very dangerous, because a single private key can decide to change the whole logic of the system, and a malicious or compromised EOA admin can decide to stop the DApp or like steal the funds. And there was an incident on Bent Finance in December 2021 that the admin like upgrade the system into a backdoor version and like take benefit from this. However, the community considers the using a multi-signature wallet as a safe option. We want to say that this scenario, is not that much safe, because limited number of persons can change the whole logic of the system. Like the other problem in this like admin type is that addresses on Ethereum are pseudonymous, and nobody can prove the identity behind the address. So a malicious team can keep enough keys in their hands to sign any transaction they need, and then like steal the money in their desired time. And like there is an incident on Ronin Bridge in which like 5 private keys are leaked, and like the attacker signed transaction with that multi-signature. The key takeaways of this research is that immutability and decentralization are like oversold in Ethereum, and like over 60% of upgradable contracts are just controlled by one or limited number of persons. Also, we emphasize that consensus override is still a choice of upgrading smart contracts, and it may happen to like L2 uh, platforms. Also, it's worth mentioning that the mechanisms we find like proxies in our research is generic and not just specific to a library like OpenZeppelin. And thank you so much. You can get in touch with me if you have any questions, and you're more than welcome to send me an email or ping me on Twitter. Thank you.